So in the last session, just to recap, maybe primarily for you, Keval, I guess, we finished the root cause analysis. We did the requirements. We identified what all concepts that we need for finishing this design challenge. And as part of that, we did the story where we did the entire experience and an overview of machine learning. We did the root cause analysis, and as I mentioned, the solution architecture. And I was checking with the entire team if everyone is comfortable with Python programming, and everyone said yes. So we would be skipping the high-level overview of Python programming, and we have shared the material for everyone's review or as a refresher if someone wants to get comfortable with Python. So these are the other learning modules that we have in our roadmap. So right today, we would be starting off with the data preparation. And as part of that, we'll be covering all of these topics. How do we select the data? And when we have the data, what type of data pre-processing techniques that we need to use? And with the data in hand, are we happy with the set of variables that we have that we can use to build the machine learning model? Or do we need to derive any additional features out of them? Again, it all depends upon the data in our hands, right? So all of that would be the data transformation or the feature engineering. And then once you have set of features in hand, not each and every one of them may be helpful in contributing some information to the model in terms of gaining some intelligence. So that's where we identify, these are the top list of features that could contribute or that could add value in learning, again, some intelligence on the topic in hand. And that process is the feature selection. So we'll be going through some of the techniques on those. So on the data preparation itself, maybe I might have slightly already spoken about what is the purpose of this one, of the data preparation. If either one of you have any different perspective, you can share your thoughts. Otherwise, we can move on why we need the data preparation.
The main reason we need data preparation is so that we have accurate data to train our models, and we have to see what features are important while training our model. So for that, we need to first find a proper data set which can work with the problem we are solving, and then later we would be cleaning the data set in a way that there are less chances of getting like errors in our actual algorithm.
Yes, yes, yes. The very first step is, again, since we need the data as part of the machine learning, we need to start off with selecting the data, what all different data sources that we need. And the things that you just mentioned about are the data pre-processing and the feature engineering parts or the data transformation part, Kevin. And when we're thinking about the data itself, in most of the applications, you might come across the quantitative data, which you are already aware of. And we covered a bit on this in our AI and ML overview session as well. We were talking about the different types of input data and the different types of output data, the target variable. So we can have purely quantitative. Again, they could be numeric, which can be represented by binary or integer or a float. And the qualitative information like the textual, which can be converted into just pure strings or the categorical type of information. The computer vision would fall under, in a way, when you talk purely from the data type perspective, it would fall under quantitative because each of the pixel is an RGB value, and each RGB value has a numerical value associated to it between 0 and 255. So all of those are integer values as well. And same thing goes or applies to the audio data as well. Over a period of time, on x-axis you have time, and y-axis you have the um, intensity of the sound strength. So that would be still a float value, the double value. Sorry, yeah. The data is the key. Without the data, there are no insights. So that's why we need to ensure that we select the right data, we perform the right processing steps on it to ensure, again, to your point, Keval, the quality of the data is really high so that we get very meaningful insights out of the model rather than some sort of like noise, which are based on just like some correlation without uh, having any relevant or relevant meaning. So now thinking more from a corporate perspective, I guess, whenever you have a problem in hand that you want to solve, typically you would fall under, you would think through these three different point of views. Well, you already have some available data. For example, on the synthetic fraud identity, you will have all of the applicants' information, like their name, SSN, phone number, physical address, email address, all of this information. That out of which, and maybe some other information as well. So you'll be using all of that available set of data to begin with. And then there would be some data that you wish you had, but you don't have access to it either within your company. That's where you will see if you can try to find that information available either in as an open source or if a third party service is providing that information. For example, if you want to get all of the historical addresses at which a specific customer has stayed on, most of the times when the customers are submitting an application, all that you will have access to is the best case scenario is their latest or their current address. But if you somehow, for whatever fraud analysis, you want to get access to the historical addresses as well, then one of the source can be your credit bureau. They do have all of the historical addresses of the customers, if they have it, but they would have placeholders at least. So from that perspective, you can integrate with the credit bureaus to get this historical addresses information. And you can try to enrich the data set that you can use for building the models, for generating the insights. And then, as I was mentioning earlier, along with the application data, you might receive maybe some information that is either very trivial or that is not relevant to the problem that we are trying to solve. So you just exclude that. It's straightforward. And yeah, so the other scenario regarding the unavailable data is even in scenarios when there are no third-party services at all that can provide the data, then what you can do is if the machine learning practice or the data science practice within the company is mature enough, and if you have resources in hand, you can try to simulate the data by generating some synthetic information about that particular nature of the information that you're looking for about the customer. So simulating the addresses would be very tough. So it all depends upon what type of information that you are trying to simulate. So that's definitely a key aspect in here. And the way this particular requirement can present itself is, well, that particular variable or that particular information that you're looking for that you do not have access to, it may not be available for all of the customers. So you would have to figure out a way in that scenario. Or it could be the scenario that maybe like 5%, 10%, some small percentage of the customers, some percentage of customers um, for whom you have the data, but you wish you have that information for the rest of the customers as well. Okay. So in those scenarios also, again, you can choose the third-party service or you can try to simulate that data. And there could be different reasons why you might want to do that. One of the uh, most probable scenario is the nature of the algorithms, machine learning algorithms that you are going to use to build the model. Some of them would present these constraints. For example, if you are thinking about simple decision trees or even the random forest, they would require you to have the information available for each and every record for a specific column. Of course, what would that mean is you would have to make choices of filling in the missing information through some techniques, some simple statistical methods like the average value, median, mode. We're going to talk about the data imputation as well, but just try to give you a quick glimpse into that. Any questions?
I had a question.
Yes.
Meeta, you can go ahead.
Keval, you go ahead. Yep.
So the main question I had was the time when we derive or like synthesize a data, how do we ensure that that data is accurate and won't cause any biases in the actual machine learning output?
Yes. I can definitely answer that, but just checking if Bitan, if you have an answer to that.
I didn't have an answer. I had actually a follow-up question to that. More than accuracy, the thing that I was about to ask was, when we are sampling our data set or we are assuming a source of data as correct, how are we making sure the correct statistical methods have been followed? Because like a lot of the times, the population from which the data has been taken from might not be really representative of what we are trying to do. So in those cases, as somebody who's more of a consumer of the data rather than somebody who's producing and like surveying the data, how do we make sure that we are doing the correct things? Like it's more like a follow-up question to what Kevin was asking. Sorry.
Okay. So let me start off with Keval's question first. How do we ensure the maybe accuracy of the data or that the data would not be biased, right? The very straightforward answer is the data would be biased, Keval, because unless in most scenarios, in most synthetic data generation methods, the data would be biased. It would be biased because most of these methods would involve trying to fit certain behaviors to specific variables and then try to construct the data out of it. The most traditional methods have been like if you want to probably estimate the age of the customers who are applying for the bank accounts, hypothetically, if you want to generate the data, let's say all that. So this is where one of the approaches that people do take is going back to your point, Bitan. Um, you can take you can take a very sample population out of the existing customers that you have, and you can enforce certain constraints like filter the data for me based on the regions like the US market, India market, or some specific countries. And then within that, okay, try to identify the mean and standard deviation. And then just your approach can be as simple as, okay, now generate a normal distribution of not the age of the customers, which follows a normal distribution with this mean and the standard deviation. That would be the most traditional historical way of generating the synthetic data. Now, even though that feels very simple, it can be quite powerful the moment when you extrapolate this to multiple features, because this is completely randomized. The only bias that you are getting in here is calculating the mean and standard deviation, which is based out of the existing sample set of customers from US. So that's a bias that you are baking in. But the randomness that you are getting is something that would work in your favor. But nevertheless, there is some bias. Now coming back to sorry, just to finish up the response to your question, Keval, there would be bias on that in terms of ensuring whether the data is accurate or not. Uh, it would not be accurate in the sense that think of generating the data as another machine learning model. Okay, I know we are talking about building an entire machine learning model for a given problem in hand, but if you think about building a model to find out what the values for that particular variable, like let's say age. Now, assuming that you have 10 other variables, you can use them as inputs to your intermediate model, which can estimate the age of the customer. Okay. So over there again, it is an intermediate model that you are using to generate the data. And again, this is purely machine learning based approach. Now you can employ a statistical based approach, just like univariate or multivariate normal distributions to generate the values. Because you can generate the normal distribution even when you have multiple variables with multiple means and multiple standard deviations. I hope that answered your question, Kuro. And to your question, Bitan, on we are going to take the sample data set. So can you please rephrase your question again one more time?
Yeah. So what I specifically was asking was like, so when we are taking a data set from any source, we are assuming on a ground level that is ground truth.
Yeah.
Now, but we are also assuming that the methods that were employed to gather that data was, like one Keval mentioned, was unbiased as much as possible, as well as the correct like range of population or the correct group of subset of the people was like people or whatever data was used essentially. So my question was like, as somebody who's more on the consumption side of this data, how would I or how would my like any team try and ensure that, like, how can we enforce the fact that the population was correct? Because like there's a lot of like cases where even statisticians make the mistake of the kind of data, like subgroups that they have created, where it's not really, it is pseudo random that rather than random, and so on and so forth.
Yes.
So that's where I was like, I had a confusion. Yeah.
Yes. So this is where, as part of the initial steps, even before building the model, you need to explore the data, try to understand the data. Once you, let's say, identify total of 100 variables as features that you want to consider for modeling, you need to understand how the distribution of each one of these variable or the feature is. Does it follow more like a normal distribution? Does it follow a uniform distribution? Does it have any tails, either on left side, right side, or even anywhere? So looking into each one of these variables, or at least some of the variables that you think are a bit more important, would give you those insights, and you will try to ask the questions of, okay, why is there a tail on this particular variable? That's when you probably take sample records which fall into that tail. That might give you the insights on, okay, this particular record probably belongs to a bucket of records which probably is under sampled. Now you can go back, if you have access to more data. Now you can go back and then try to capture more of the data. So that's where, as a data scientist slash data analyst, when you explore the data, you need to identify these insights, or ask questions and generate the insights and try to take measures accordingly. Vedant. Okay.
So are you like what you mentioned? I understood that. Are you like, do you mean that we should also include things like p-tests and p-value checks in the same thing, or yes?
So t-test, okay. Now, the moment when you said t-test, you need to compare it against something else.
Correct.
What do you want to compare it against?
So maybe like the distribution of some standard data set that is like maybe has been vetted prior to this, like it has been correctly vetted. And then I know it sounds like a little bit of a circular like explanation of what I'm trying to say. But then yeah, I think that is where I have like a question with statistics in general, because it's a little open-ended, especially when it comes to like analyzing distributions. Because yes, I would prefer that it is a not like a uniform distribution or a normal distribution. But what if the data is such that it is skewed? And if it is skewed, how do I know that I have the correct data instead of I've made a mistake in gathering my data?
So, yeah, exactly, Pitan. Particularly for the real world problems, there wouldn't be any correct data. Right? You have to create correct data for your problem from a data perspective. And
So
that's where,
I wanted to chime in.
yes, please.
So I am going to share a perspective that I wanted to validate. So 10 or 12 years ago, before the advent of big data computing technologies, I remember we had to sample the data primarily not because data wasn't available, because we couldn't store and process that size of data. The infrastructure and the technology wasn't available. When the technology did become available, then we had the option of using the entire data set that was available to us. So for example, if I'm trying to do something with customer data, and I'm the company that owns the customer data, I actually do have the entire customer data available to me. So I wouldn't have to sample. I can use that entire data set. And if I wanted, I could use all of the attributes and all of the transactions for the last X number of years or so. So my understanding is that this problem that Keval and Bitan brought up shows up only when we are trying to either do a sample or when certain data sets or certain attributes are not available and we are trying to synthetically generate. Is that a correct statement?
Yes. Yes.
I sort of disagree with the statement because I understand what you're saying, Sandeep, but then I would probably give you an example of what I mean. So when Google Pay had come to India for the first time, Google Pay came as the app called Tez. So when Tez had come, Tez was a rage in in all universities back in India. Not because Tez was great. It was great. Obviously, the infrastructure was great. We hadn't used UPI like this before. Like we had Paytm, but it was like, for the lack of a better word, Paytm at that point was shit. So like having a UI that was this clean and having something that made so much sense was great. But for students, it became like an alternate way to gain money because we could make transactions of 200 rupees and get back 51 rupees each day. So basically there was a cycle going on in most universities where I would send you money, you would send him money, and then he would send me money, and we all would make 150 odd rupees or so, like within three of us, by just circularly transacting the same money over and over again. And this went on for 6 months. And then I had read a case study where Google had considered that Tez was a huge hit in India, especially in the what they called the millennial generation, which was like, and they were proven absolutely false 4 months down the line when they realized the moment they took away and then reduced that value from 51 rupees to 11, suddenly the numbers dropped like crazy. So like Google Pay still has it. Like when the first transaction that you do, you get back some amount of money. I think it's 21 right now or something. But they've like same thing happened with Uber when Uber was coming into the market. But then I think Uber had a lot more data. So Uber did not face the same issues. The thing I was trying to highlight was that when I'm starting off a problem in an area that has not been maybe like my company or the company I'm working for has not delved in before, so to speak, or it's something new to us. While we have a lot of data, how do we make sure that all of that data represents a correct trend rather than a falsehood that has become a part of the trend?
You confirmed what I just said, Bitan, that in this example, when you're starting out and you're trying to predict something, you don't have data.
Correct.
So, which means that for you to be able to predict that, you need to somehow use data that is either synthetically generated or some sample set of whatever limited data that you do have. So that's what I was saying as well, that the other point I was making is, let's say 1 year fast forward after Tez was introduced, Google had all of this data at its fingertips. But depending on whether they chose to compute and process all of that data to predict whatever they were trying to find out, or if they chose to create a sample. So there are two scenarios that exist. At the beginning of the process, when they did not have the data, they would have had to do prediction based on some synthetic data or some other sample, which is similar, based on which they predicted. So they must have come up with the number 51 based on some rationale, right?
Okay.
So that's what I was saying, that anytime you don't have data and you have to try to create synthetic data, or if you don't have the processing power or you choose not to use all of the data available to you, that's when this issue manifests. But if you did have all of the data and you could process all of that data and use that for prediction, I was just trying to confirm that you wouldn't have these kind of unavailability or bias in the data.
Okay, yeah, makes sense. That makes sense. Yeah.
Actually, even in that scenario, Sandeep, when you plot out the distributions for each of the variables, even when you have, let's say, 1 billion records, even then there could be scenarios where you may not see a proper uniform distribution or a normal distribution. For it could be for different reasons. Maybe it's just that that bank X they were probably just giving out, or they're just marketing only for one particular race within a country, and they have very less customers from some other race. In that scenarios, even if you have 1 billion records, then bias in the data can manifest.
Yeah, great point. Thank you, Madhu, for that clarification.
So,
I had a quick question, if you guys
yes,
don't mind.
please.
And I don't mean it in a, I don't know, if it comes out wrong, please let me know. I do not mean it in any way. So since both of you have worked in SVB before, did you guys, what Madhu just mentioned, did you guys see any of that as part of SVB? Because SVB's client base was primarily hyper growth startups in the Silicon Valley. Like, was that something that you guys faced at all? Like, I'm just talking from a perspective of what you guys thought about the situation.
I was at SVB, Madhu was never.
Oh, sorry. My bad.
But no, we did not see that, because most of the decisions SVB used to make were not data driven. They were relationship driven.
Okay.
So a lot of the decision to earn a client, these clients were not lending clients, these were deposit clients.
Correct.
So when a VC decided to fund a certain startup, because SVB had 70% of the US VCs banking with them, the VC would say, Bitan, I have decided to fund you. Now you should open your account with SVB.
Okay.
So the bias actually comes in when you are lending data more than when you are getting a deposit account. I'm not saying it wouldn't, but typically a lending scenario is more likely to have bias than a deposit scenario, if that makes sense.
Okay, makes sense. Yeah.
And in general, if I have to step back and then try to either paraphrase your question, Bitan, and maybe we can discuss about that. The aspect of any bias in any of the decision-making systems in the finance industry, did we see that in our experience, right? So there would be instances of such scenarios, Deepa. That's when they would become quite popular in media. One of the example was when Apple Pay came out a few years ago, 2 to 3 years ago. Apple's ex-founder, Steve Wozniak, he and his wife, both of them applied for Apple card, Apple card, credit card, and both of them got the cards. The only difference was Steve Wozniak got a credit limit that is almost 18 to 20 times higher than his wife. So he got pissed off. His wife, of course, probably got pissed off, and there was huge thing on the media on how that machine learning model or that decision making system was biased towards, in this case, gender.
Right.
Right. So that's why there was some investigation went on to, or more like an audit that has happened to ensure that if the model was biased towards gender or not. So that was more of an instance. But to your question, the regulations on the discrimination, particularly in finance industry and also in healthcare industry, they are becoming quite tighter and tighter.
Okay.
So from a data science or machine learning practice perspective, most of the companies are heading towards creating creating sort of like procedures
Compliance.
or the techniques
Okay.
in place while building the model itself,
Mhm.
ensure that there is no discrimination against the information like gender, race, age,
Correct. Okay.
whether you are employed or not. So some of the sensitive information, sensitive variables that we should not, that the company or the industry should not discriminate
Against.
against. Yes, yes. So the end.
Add one other perspective there, that when a company, so because we're talking about lending, when a company makes lending decisions, the company could be lending to an individual or the company could be lending to a business. So the regulations for individuals is very different from the regulations for companies. So CFPB, as an example, which is one of the regulators for consumer protection in the US, that has gotten very strong over time. And companies who are in the lending business, they have to make sure that there is very little bias in their systems, or no bias ideally. And they also have to be able to explain if they take any kind of adverse action against a certain company. So I asked for a $5,000 loan, but you only gave me a $3,000 loan. You have to explain why you made that decision. So it is sort of reinforcement learning that there are incentives and penalties built in the process. And those same regulations, the same rigor is not applied to when you're doing commercial lending. So hypothetical or supposedly there could be a lot more bias in commercial lending use cases than there is in consumer lending use cases, because the regulations have steadily been becoming more and more rigorous.
Excellent. And just because there is so much of attention on ensuring that the models should be unbiased or non-discriminatory. So that's where the entire machine learning field, particularly the uh, subfield of non-discriminatory models, or the the mechanisms to ensure that if there are any sensitive variables that you are using as part of your training data in building your machine learning model, the techniques within the machine learning model building pipeline itself, incorporating these techniques as one of the steps before you deploy the model into production, and ensure that against these variables, your decisions are not biased towards one specific values within that variable. For example, one specific race. Okay. So in here, just to take a step back, you're not supposed to use these variables in your model. The moment when you use these variables in your model, the decision making, the target variable can depend upon, let's say, the race, right? So that is very straightforward. And that's what maybe until like 5 to 8 years ago, people, that's what the models used to do. Just don't include any of the sensitive variables in building the model. And when you look at it now, so that is given. That is by default, you're not supposed to consider any of those variables. But we're taking a step further to check if any of the other variables that I'm using in my model building, are they correlated with these sensitive variables?
And could lead to some kind of biases.
Exactly. So the bias would manifest in a indirect approach.
Correct. Okay.
So you are basically checking for this indirect biases. Yeah. So in the data pre-processing, I guess to some extent, we did the questions that you asked, Bitan, and Keval, how do we ensure the quality of the data or the accuracy of the data is a bit high? So that's where, again, as a data analyst or even a data scientist, you need to spend decent amount of time to understand the distribution of the information in each and every variable that you are considering. So not only the distribution, but also looking at the some of the summary of the statistics. Like if I have total of 1 million data points for one particular variable, do I have all of the information available? Is there any missing information within that? And then trying to get some thoughts from the subject matter expert. For example, if we are trying to build a model for synthetic identity fraud, ensuring that we are working closely with an expert like the investigation team who knows about some of the variables information. It doesn't have to be the investigation team. Since we are talking about the input features as well, any of the um, business analysts who knows about the specific variables. For example, let's say the race itself. What all different values can it take? Does it make sense? Just to ensure that everything looks good from the values in the variable perspective. And yeah, we need to and not just anonymize. Again, some of the variables you just need to straight out remove them from the modeling. And in some cases, if you are sharing the data with others, because in big corporations, you always end up collaborating on any project, you would have to anonymize some of the sensitive data, even if you're not using some of the columns for modeling purposes, but uh, just to maintain the record for record keeping purposes to track the records, each and every records in the training data. We did discuss about the data imputation. I think, okay, I actually would like to have this more as a conversation. uh, so whenever there is any missing information, the straightforward or the easiest approach for you would be just to remove that record. But again, this you can use this approach only if you have access to lot of data. If you have only 1,000 or maybe let's say 100 records and 70 records have one of the feature missing, you cannot remove all of the 70 records. But that would be the easiest one if you have an option. Now, inserting a derived value. For example, the most commonly used method is replace it with some statistical value like the mean, median, or mode. Most of the times it would be the mean. And we discussed about this one as well. Create an intermediate machine learning model. Try to build a model to predict the value of the missing variable based on all of the other variables that are present. So this is where it can become a bit cumbersome because now you need to ensure that each and every one of the other variables are available for all of the other records. So basically you can end up in doing this more like a recursive process. It can take a bit of time, but again, if the problem is very critical for you and if you want to impute a bit more precise values for each of the records, then this is definitely one of the best approaches. I think Yeah, we again briefly discussed about this one as well. If you have access to, let's say, billions of records, uh, even if you do have access to the computation power to use all of the billion records in building a machine learning model, sometimes you probably don't have enough time uh, uh, to do not only just the exploration, because even the training time is going to be quite high, right, when you use the entire data set that you have in hand. And definitely not a good idea for your first version of exploring the data as well as building the model. Okay. Once you get decent confidence after exploring the data and building the model, then you can definitely increase the sample size to ensure that the quality of the model and representation of the data that you are using as part of training goes up. It becomes more of a global population. Out of, let's say, 1 billion records, maybe you can use 100 million or 500 million records. Okay, now these terms are a bit interchangeably used, but the most popular terminology is the feature engineering. In the previous steps, we were discussing about just enhancing the quality of the data, right? And we are not trying to change or derive some information out of an existing variable. But in the next step for the data transformation or feature engineering, we would be trying to create a new variable out of an existing variable. So basically do some sort of transformation. And there are different ways and different methods that we can do this entire feature engineering. So looking into the scaling, are you aware of any of the scaling methods in data preparation steps?
Do you mean like normalization and standardization?
Yes.
Okay.
Yes. Yes. What is data standardization or normalization data?
So normalization is basically like both of them do technically the same thing, just that the ranges differ. So instead of having like a wide variety of values, I try to push the value down into some like a sort of a ratio value or some sort of a nominal value, which is, I won't say nominal value, some sort of a statistical value, which is more manageable and explainable rather than having a wide range of values. So I basically limit my range to either like between -1 and 1 or 0 and 1, which essentially makes it easier for me to see the data in a better sense and also handle computations in an easier fashion, as per my understanding.
What is the name of that technique?
Like it's scaling in general, but I think when we do it between -1 and 1, it's called normalization, and when it's 0 and 1, then it's standardization, if I'm not mistaken. Or it's other way around. I might be confused on that. Sorry.
Keval, any thoughts?
So normalizations, like how I would understand it is like giving it in a form that we can explain it in the form of a percentage. So it should be between 0 and 1. For standardization, it can be a standard value. So it can be ranging from, instead of 0 to 1, it can be ranging from a different standard value for that specific data set.
You are right for the normalization, and it's typically called as min-max normalization, and it would be between 0 and 1. So in here, what you're trying to do is, again, both of you explained this very well. You're just linearly scaling it down to fit into the range of 0 to 1. And again, linearly. So that's a equation. If x is your raw variable value, you do x minus x min by x minus x min. So this is going to be a constant value, right? And this is a constant value. So basically you're shifting the value in here. X minus x min is shifting. And then you are dividing the entire value with some constant value. That is more of diminishing the value. So think of it as y is equal to mx plus c, right? So which is a linear or a straight line. So you are performing a linear operation on your raw variable to get a new transformed variable. So that's your min-max normalization, where you're doing a linear operation. On the other hand, standardization is a non-linear operation. Okay, it's not that you can have it for any other range. It's when you want to fit the variable x, whatever distribution that you have, to a standard normal distribution. Okay, so what that means is this is your raw variable value, and you are transforming it to get z by doing a linear operation on couple of metrics which depend upon x. Okay, essentially it is, since sigma is not constant, sigma is not a sigma depends upon x. Right? Since it depends upon multiple values of x, let me be a bit more accurate. Multiple values of x, not just one single value. So you are trying to fit or transform the value of x into a range of minus infinity to infinity. Not just 0 to 1, but minus infinity to infinity. But when you look at the distribution, it will have a mean of 0 because you are subtracting it with the mean of x, and its standard deviation would become 1. So that's why it will become a standard normal distribution. That's what your z will be, z will be. Okay. Now, any guesses on in which scenarios you want to use normalization and in which scenarios you want to use standardization?
Um, you just added the depends on algorithm. So maybe based on that, if I think like for the problems like linear regression, we can use normalizations. But when there are exponential distributions, we use standardization.
Okay. When you say exponential distribution, something like logistic regression. Okay. 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 Why would you want to use standardization for logistic regression?
Um, I'm not that sure, but probably because the way in which the distribution would be shaped, it would be better to use standardization as that would be more accurate for that.
Any thoughts, Bita?
So from the perspective that we usually say that normalization is more of a linear scaling process and standardization is more like non-linear essentially. I think when we are doing normalization, we would be doing normalization for cases where we want the data sets to be scaled along the same range essentially, or what I'm trying to say is like if I have multiple features and I want them to be represented along the same range or the same distribution, so to speak, then I would use normalization. While if I wanted to try and see how like various features have various distributions, and based on those distributions, how the each cell or each value in the data is like varying, then I would do standardization. Like, so I don't know if I'm explaining it properly. It sort of makes sense in my head. I don't know if I'm explaining it properly. Uh,
So you're saying that it may depend upon the other features.
Correct. Yeah, sort of. Yeah.
Okay. Okay. Why do you think so?
So I think that is one of the main features of linearity, right? So when we are doing linearity and non-linearity is when I have multiple things affecting the curve. Let's say we are talking about a curve. So we have multiple things affecting the curve in various different ways. While linearity it has only 1 degree of freedom essentially. So there's only 1 degree of freedom that is essentially affecting the curve. So that's why I feel like normalization should be in like explained in that way, and then standardization in the other way.
Got it. I like the thought process, Bitan. I do.
Okay.
Thank you. But unfortunately, that's not the reason.
Okay, sure.
So because when you think about all of our features, you do, so from the terminology perspective, you do call them independent features, right? All of your inputs, you assume that they are not dependent on any other independent features, right? Of course, in practice, there would be dependency, but in terms of how you model things, you'd consider them to be independent. So from that perspective, the behavior of each independent feature is not impacted by other features. So the answer is actually quite simple when you try to think purely from. So this is the output range, right? 0 to 1 for normalization. And for standard normal distribution, it's minus infinity to infinity. And you have a standard normal distribution. Give me 1 second. Yeah, standard normal distribution. In this, oops. So that's 0. And sorry, it will go on somewhat like that. Not below the line, but just above the line. So minus infinity and a plus infinity. So as you can see, let's say if the raw value originally had some values between, let's say, minus 10, okay, and maybe 35. Okay, so those are the min and max values. Now, what will happen when you do the normalization? What would be the minimum value and what would be the maximum value? Yeah. What would be the minimum value in standard normal distribution? And what is the maximum value?
-1 and 1.
Nope.
Minus infinite and infinite.
Yes. So these are the limits, minus infinity and infinity. Of course, minus 10, this record will not become minus infinity. This will not become plus infinity. The thing that will happen is minus 10 might end up fall somewhere in here. Plus 35 might fall somewhere in here. Okay. The thing is, there is a lot more gap between these 2 points. Now, in standard normal distribution compared to earlier. Earlier, it was, so whatever distance that you see between them, in comparison to the other points that you have, in comparison. So that is a key in here. Since this is a linear transformation, let's say I have minus 10 and let's say the next point is 0. Or no, maybe next point is minus 5. Okay. Now 0. So because this is a linear operation, let's say -5 became 0.1, hypothetically, okay? The distance between -10 and 35, it became 1 now. And the distance between -10 to -5, it linearly became exactly the same. It scaled down with the same amount, same ratio, because it's a linear operation, right? It will go down to the same value. It will go down by the same value. Whereas in a standard normal distribution, it goes up or down by different amount. Each point can compress or elongate, thereby reducing the gap between them or increasing the gap between them. So the way it would be helpful is if there are scenarios where you want some of the points to be closer, they can become closer over here in this range. If the for farther away points, the range would become a lot more wider now. The distance would become a lot more wider. So it would help us try to separate two groups of data, one group of data to come together and the other set of group of data to elongate. That way the distance between them becomes a lot more wider. In a way, think of them as you want to identify -10 as an anomaly. Okay. If that point is somewhere in here, it's very from, so you know that the standard deviation in a standard normal distribution, the very first standard deviation is is around 63, 65%. I forgot the exact number. You are on mute, Nitan.
Yeah, it's 63.5 if I'm not mistaken.
Yeah. And the mu plus or minus 2 sigma is around, I believe, 85%, 83 to 85%. And then the 3 sigma is around 99%, right?
I think it's 97, and because 2.5% is left, 97.5 approximately.
Okay, yeah. So the thing is, the moment you are farther away from sigma, your point would become would present in at much farther distance, thereby increasing the distance between that point and some of the mean points, a point in the middle. So you'd be able to separate them out very easily. Okay. So it would be helpful for us to group the data accordingly. All right. So I hope that helped. Um, Now, decomposition. So we discussed about the scaling. Any idea on what the decomposition is? Oh, I think I already have split the variable into multiple components. Any examples?
Maybe positional data, maybe breaking up into X and Y coordinates, something similar.
Perfect. Yeah. That is definitely an example, Pita. Yeah. In fact, from one perspective, it is in a way that, so taken any image, any color image, right? It's an RGB image. From a technical perspective, it's called as an RGB image because you're on mute, Pita.
Because it's got 3 layers of colors essentially, or 3 colors essentially, which makes up the.
Yes. Red channel, green channel, and blue channel. So that's why any color image that you take, it would be a 3-dimensional data. X-axis, Y-axis, and then the Z-axis would be your RGB. So that's your R, G, and visibility. Okay. So if you think there is some unique information in one of these channels, then it's always better for you to focus primarily on that channel, or at least try to extract that separately so that you gain most information out of it. It's very meaningful, particularly uh, in healthcare applications where you're trying to, let's say, um, do any studies related to, let's say, imaging. Let's take image. When I say imaging, the PET scans. Not sure if you know what a PET scan is. It's a positron emission, I think it's technology, where a radioactive material is injected into your body, and that material will glow like a bulb under under light. So when light is exposed, and you'll be able to see that material wherever it attaches to your body. So it's very powerful technique that people use in healthcare industry. So over there, in this example, usually it would glow in white color. So not, you just need to look out for the bright color over there. But there would be very similar applications where you would paint some of these markers, the terminology is markers for some of the reagents in, let's say, green color as a photoluminescence. And you like to capture those specific reagents. And you can capture that very easily if you look into the green channel image in that specific example. Okay, so timestamp is one of the most widely occurred variable or the data input that you will see as a machine learning engineer, as a data scientist. Okay, now in this example, what did you do to decompose the data?
I think on a high level, like doing date and time would make more sense from a date time, because I think this is a date time variable.
But what do you mean by date and time? Because
So
if date is, yeah, please go.
Yeah, so what I meant was by time, I mean time of day. So essentially like 15:05 would be like 3:05. Like that could be relevant because it might be maybe indicative of when a particular thing, like when this data was taken, if that is like a peak time or not an essential time. So we could give lesser weightage to that part of the data, or maybe that row of data, essentially entry of the data. And then date would also be essential because maybe like since it's December the 3rd of 2018, the year would be relevant because if there was something specific that happened on the year, and also the month, because usually December is a month, like especially for banks, like December and March are 2 months where like there's a lot of activity going on because Christmas and a lot of things, and March because, well, April is coming and the end of the financial year. So I guess maybe those might be specific things that we might be looking at based on the date time data. Uh, I mean, date could be significant on day of the week as well. Like if there's a particular day of the week when, like, I mean, we could draw a lot of insights from this
Exactly.
based on what we want. Yeah.
Yep, exactly. Those are the main things. Although on that time you did not go into the details, but I'm sure you had it in your mind. It just it did not come out apparently, I guess. So for the date, as you mentioned, you can create all of these other features, that the ones that you called year, month, day. You can derive even the quarter, right? You can derive even the week within that month. And you can even derive what weekday is it. Is it Monday? Whatever. Okay. And on the time you mentioned 305, but still 305 is not a meaningful feature, Bitan. Right. So you need to go into something that is more representative of an integer value or something, or a categorical. In this case, rather than categorical, integer does make a lot more sense. So from that perspective, hours, minutes, or seconds. So do you guys know what an epoch time is? Okay, please go ahead.
So as per my understanding is one epoch is when, so I'll talk about it from a deep learning perspective. So basically one epoch is when like one round of training has completed essentially.
In deep learning, no, this is not the same epoch.
Okay, it is not the same then. But I think it will be something similar. It would be one iteration of something, because epoch, as per my knowledge, it is sort of one round of something or one iteration of something, as per my understanding. If it's, I'm not incorrect, sorry.
It's like you have the absolute zero time, which is 0th year, 0th month, 0th day, 0th second.
Okay.
And everything from there, when you measure the time, everything from there in seconds as integers. Okay. So that would be the epoch time.
Okay.
Okay. So aggregation, pretty straightforward. As the name suggests, you aggregate data to create new features. Okay. A couple of examples. Instead of looking at each and every time the customer has logged in, now you probably want to roll it up as an aggregated to identify, okay, number of logins in a week, in a month, in an year, something like that. And in some cases, you might want to roll up from one level to another level, like if a customer has 3 credit cards. Okay. Maybe the customer logged in as in one personal card, let's say one corporate card. Once logged in from the personal card account and another time logged in from a corporate card account. Probably you want to look at it from, instead of each account level, now you want to look at from customer level, which means it both of them are included as part of count or the value. Oh, sorry, I think the animation. So let's talk about the encoding. Why do you need encoding?
I think one particular way, like reason why we do it is because when you have categorical data, it's pretty difficult to like quantify that in any way. So like one of the basic ways that I can think of is like, suppose I have month data, like which month it is. It does not make sense for me to pass January into a machine learning model, because the machine learning model does not really know what to do with January. Instead, if I give it like an integer value or like a categorical value corresponding to that, like we got cat codes or like one hot encoding, whatever you want to call it, then the machine learning model at least has a sense of all right, like this is the nth month of the year, or this is the whatever, like whatever value that is essentially. Yeah.
I think, yes, absolutely right, Bitan. Just taking that particular statement a bit more in depth, when you said that computer doesn't know what to do with the word January, it knows the word January when, from a character by character perspective, it knows what each character is. It can even try to relate the January word when you try to give it a reference of, okay, these are the months from a calendar perspective. But in machine learning, what we are trying to do is we're trying to calculate or perform operations on our input data to derive some insights. Now, can we do any operations on our textual data? So no, so that's the roadblock for us. For us to move from that point onwards, we want to convert that textual data into something which the computer can try to calculate or perform operations on. And that is the numeric data. So which means now we need to convert our qualitative data into numeric data. That way the computer can perform operations on it. Okay. Yeah. So most of the times it is represented as part of the textual data. Yes. We discussed that. Now, okay. We did say that, okay, we have to convert the textual data into the numeric data. How do we do that? Do you guys, are you guys aware of label encoding? Okay. If not, then typically what you do is, let me take an example. Let's say this is gender is one of our variable, one of our feature. And these are the values that it can take, or it takes in our set of data that the sample data that we have. And this is the record ID. Okay, this is a record ID, row number 1, row number 2, and so on. In label encoder, what you do is, it's something like, it's exactly like a hash map. Okay, you take all of the unique values from your feature, which are these, and then try to give them some integers, like typically starting from 0 and then until the length minus 1 of the unique values. Okay, so that's your hash map, right? That's your key and this is your value. Use that to update this data now. For your record ID, row ID, these are my label IDs. And now you have a number. You replaced each of the text data with a number. And now, okay, these are numbers. Whether can you perform some operations like 0 into 0 or 0 plus 1? Does 0 plus 1 or 0, maybe 1 plus 2? I think since we do not have a value of 3 in here, I could not take that example. Let's say you have a value of 3. Is 1 plus 2 equal to 3? In this case, definitely not. It's not meaningful. But at least what the computer can try to do is it can try to hold those things, and the algorithms that we designed, the machine learning algorithms that we designed, they can, when you share the information that this is a categorical ID or this is a label encoder, that algorithm will process it accordingly. Okay. Instead of doing the operations like 1 plus 2 is equal to 3, it will avoid doing those types of calculations. So, now you have another option, which is one-hot encoder. This is where now in this example, you have a total of 3 unique values. You would expand this one now, which means, actually taking a step back, in label encoder, you had the raw variable was gender, and the new variable is, in this case, let's say label ID is the name. Okay. But in one-hot encoder, you now create 3 unique values, which means 3 unique columns. Okay. Whenever for each record, since it can have only one value, so only one of this is going to be 1 and the other is going to be 0. Okay. So as you can see, in this information, you see a lot of zeros and only few ones. Of the ones would be the exactly number of records. So this type of data set is called as sparse data, where you see data here and there only. So the great thing with this data is the information is very meaningful. 0 and 1 have exact meaning to it, right? That whether it's present or not present, more like true or false. Whereas the downside is it's highly sparse data, which means if you take, let's say, customer ID as an example, hypothetically, or even something like customer name, since you can have millions of unique names, you are going to create millions of new features. Would they carry significant meaning? I mean, would it, what would be the downside of creating millions of columns like that?
Lots of processing. So like for no reason whatsoever, essentially.
Yes, exactly. Exactly. So you need to be very careful in, using what type of technique is more relevant for what application and what feature that you are trying to encode. Okay, now coming into the feature engineering. Okay, so essentially what they do is, oh, we are at 5 o'clock today. I think maybe actually this is a really good point for us to uh, stop in this session, Bitan and Keval. We're going to pick up from here, do the feature engineering, feature selection techniques in the next session.